All right, so last time we were talking about the ions, naming ions. Then before that we were looking at binary molecular compounds. Right? And then before that we were looking at isotopes. Right? Well, if there are no questions, then we're going to continue. Where did we leave off? Ionic compound. Basically, the name ionic compounds, we just named the cation and the anion, so we just learned a bunch of ions, but there are more. And so let's continue on with the ions. We have the acid anions and acids next. Talk about naming these. Acid anions, when we think about H+, H+ is the hydrogen ion. Hydrogen ion or the hydrogen cation, or it's called the proton, or it's an acidic hydrogen. So when we see H+, we associate that with acid. In fact, that's what we consider acid, or H+. And we have little variations of things. So do you know what this is called? CO4 3-. Phosphate. And so if we take a phosphate and add an H+ to that, so H+ plus a phosphate, we get this species, which is HPO4. Now, this is a +1, that's a 3-. So +1 and a 3- will give us a 2-, HPO4 2-. And we call this an acid anion because here we're taking acid and combining it with our anion to form an acid anion. This acid anion is called monohydrogen phosphate. Monohydrogen phosphate. It turns out that we can add two acid hydrogens to this. So, for example, if we take two H+ and a phosphate, like this, then we'll form H2PO4. Can you guess what the charge on this one's going to be? H2PO4 negative is correct. And can you guess what the name of this one's going to be? This one's going to be dihydrogen phosphate. 2 words, dihydrogen phosphate. All right, if we take 3 acid hydrogens, and so I'm going to take 3 H+, or just 3 hydrogen ions, and add that to a phosphate, then I'll form this, H3PO4, and the charge on this is going to be neutral. It'll be 0 charge. What would you call this? What do you think you'd call it? Yeah, you would think you would call it trihydrogen phosphate, but it's not called trihydrogen phosphate. It's called something else. What it's called is, it's called phosphoric acid. And so this is the situation. These two are acid anions. Anions have a negative charge. And, acid anions. However, this is just called an acid. Acids are neutral. They're not going to have any charge. And we're going to stop here because we aren't going to add a 4th one to go positive. We're just going to stop at neutral. This is our acid, which is phosphoric acid. And so if we take our regular anion, which is phosphate in this case, we can make these 2 acid anions and that acid over there. Okay, let's do another example of acid anions. let's pick another anion. So for example, let's pick sulfate. What's the formula for sulfate?
SO4.
SO4 2 minus is correct. That's good. This is sulfate. And so here's our anion, and so we can form an acid anion by taking acid, H+, and then adding it to our anion, sulfate. And that's going to form HSO4. The charge on HSO4 will be -1. Just negative. We don't write the 1 usually. So -1. What's this called? You would call it monohydrogen, or you would think you would call it monohydrogen sulfate, but it's not. In this case, it's just called hydrogen sulfate. And so why is that inconsistent? I mean, for example, over there we have monohydrogen phosphate. Here we're just going to call this hydrogen sulfate, not monohydrogen sulfate. Why isn't it consistent? The reason it's not consistent is because what would dihydrogen sulfate look like? If this were monohydrogen sulfate, then dihydrogen sulfate would just be 2 H pluses in the sulfate. The 2 H pluses in the sulfate will form H2SO4. Now, is H2SO4 an acid anion, or is it just an acid? It's an acid. And so there's only one acid anion, therefore we don't need to differentiate. Here there are 2 acid anions, and therefore we have to tell, we can't call them both hydrogen phosphate. We have to call one of them one name and the other another name. Whereas there's only one acid anion here, and that is hydrogen sulfate. This one gets a different name. This one is called sulfuric acid. And so if there's only one, then we don't have to use a prefix, mono, di, etc. If there's 2, then or more, we're going to have to use a prefix for the acid anion. And so this is just only one acid anion. And this particular acid anion goes by another name. Do you know the other name for this one? This has the common name bisulfate. Bisulfate. And so either of these 2 names is fine, hydrogen sulfate or bisulfate. Sometimes a common name is more common than the name derived from nomenclature rules. And so let's take a look at another one. How about carbonate? Tell me the formula for carbonate. Yeah, CO3 2 minus, or CO3 -2. There's a little convention about what goes first, the negative sign or the number. So for ions, we usually write the number first, followed by the negative sign, or the positive sign if it's a cation. And so this would be carbonate. And we can generate the acid anion, HCO3. What's the charge on HCO3? Negative. And this would be called? Yeah. Hydrogen carbonate. Again, we wouldn't use mono here because dihydrogen carbonate is an acid anion, or is not an acid anion? Is not. So this is just going to be hydrogen carbonate. Hydrogen carbonate also goes by a common name. Do you know the common name for hydrogen carbonate?
Bicarbonate.
Yeah, this is called bicarbonate or bicarbonate. Bicarbonate is in like baking soda or baking powder. And then finally, if we go dihydrogen carbonate, we don't call it dihydrogen carbonate. Do you know what we call this? Yeah, this one's going to be called carbonic acid. So those are the names for acid anions. The acid anion name is just your basic anion name with the word hydrogen before it. Depending on how many you have, it could be mono, di, etc. For acids, acids are interesting because all acids will have the same cation. Same cation, which is H+. The only difference is the anion is different anions for different acids. You know? So we had carbonate, we had sulfate, we had phosphate. How many different types of anions are there? You know, when you look at all the anions we covered, there are only 3 types of anions. You know what those are? The 3 types of anions that we looked at. And so the name is based on the anion. Therefore, the name is based on anion. And so the 3 types of anions are the ones that end in IDE, the ides, and then the ones that end in ATE, and the ones that end in ITE. The difference between a D and a T is T means it contains the element oxygen. When we have a T here, these are typically oxyanions. Typically, there are exceptions, but and when we have a D here, it's usually monatomic, but there are exceptions there. And so for the acid, it's just based on what the anion is. So if the anion ends in I, an example would be like a chloride. Then the acid is just the H cation with the chloride anion, so it would be HCl. It just needs one H plus to balance out the charge. And the name for this is simply, we do this. We add the hydro prefix in the ic acid suffix. And so the name for this one would be hydro, and then chlorine, but we're going to change the ending to ic. And so it would be hydrochloric, or chloride, and change the ending to ic, chloric acid. So this hydrochloric acid. Okay. Chloric acid. Give me an 8. An 8 that we haven't seen. Yeah. How about nitrate? Nitrate has the formula of what? Formula for nitrate. NO3 minus. So nitrate is NO3 minus. So what are we going to do with the acid name? Well, the acid name is even easier. So the acid will just be the H, and we only need one H. So we aren't going to call that monohydrogen. So we're going to label that. And so all we do for the acid name is just change the anion name to ic acid. And so if we have nitrate, then we're going to change it to nitric acid. So this is just going to be nitric acid. Nitric acid. How about nitrite? What's the formula for nitrite? NO2 minus. This would be nitrite. So if we add acid H to that, we'll just need one to complete it. So it'll just be HNO2. So what's the name of that? Well, what's the name of that is we just change the anion name to not ic, but aus. I'm just going to change it to aus acid. And And so nitrate gets changed to nitrous acid. So this is nitrous or nitrous acid. Are there any other categories of anions? We have the ides, the eights, and the ites. Is there anything else? No. Although your book is going to have 2 more categories, which are unnecessary. And we can see that. That it's going to be unnecessary. This needs 3, all you need, rather than 5. The book has a different approach to nomenclature. Fine. Okay, so let's just do some general examples here. What is this called? Is this an acid anion or an acid? This is an acid, and therefore, you know, an acid, this has got H+, and then what's the anion here? The anion ClO4, the charge on it is minus. So what is ClO4 minus called? Yeah. What is chlorate? ClO3. And this is ClO4, therefore this must be perchlorate. Perchlorate. Well, perchlorate ends in 8. If it ends in 8, then what do? We just drop that and replace it with ic acid. And so the name of this acid is perchloric acid. Perchloric acid. Okay, let's do one more example. How about this one? HClO. What is that? HClO. Well, HClO, this is the H plus cation and the ClO minus anion. So what's that anion name? Yeah, that's good. This is hypochlorite. Well, hypochlorite ends in ite. So what do we do if it ends in ite? We change it to ous acid. So this is called hypochlorous acid. Hypochlorous acid. And so this naming acids. Go back to the PowerPoints here. And so we pretty much know the names. That's all the anions that we're going to encounter. And so we'll just do some examples. I think we did this one. Let's see. All right, did we do this one? Ammonium bromide and ammonium sulfide? Yeah. Did we do aluminum oxide and barium nitride? Yeah. Okay. All right, we'll just continue. These are just more examples of naming ionic compounds. So FeCl3, we can tell what that is because it has the iron But iron, there's two choices of charge, it turns out. There's +2 and +3. Which one is it? It's got to be +3 because we have 3 chlorine ions, and each chlorine ion is -1, so it's chloride. And so it must be iron 3 chloride. That's the example there. Write the names of the compounds below. And so lithium is Li. Is that fixed charged or variable charge? Fixed charge. And the charge on lithium is +1. Good. And bromine, is that fixed charge? Yeah, and that's going to be bromide. So this is going to be lithium space bromide. Bromide. Lithium bromide. Right. Okay, the next one, what is Mg? Magnesium. And this is going to be an ion. What's the charge on the magnesium ion? +2. Because iodide, each one is -1. And so one thing that people get mixed up with is that subscript 2. What does that subscript 2 mean? Does that mean we have iodine, elemental iodine, present? Because if I look at I2, we call this iodine, and that's the element, and it's a diatomic. But if I have MgI2, it's not iodine. These two things are not the same here. I should put the X here. They don't represent the same thing. When I see MgI2, this is what I visualize. I have one Mg2 plus and then 2 iodides. Each iodide is -1. I don't have a molecule of iodine. There are no molecules of iodine in this is called magnesium. What is it called? Is this called magnesium diiodide or magnesium iodide? This is called magnesium iodide. And so why don't they call it diiodide? Because, we have 2 iodines here, so shouldn't it be called diiodide? And the reason it's not called diiodide is because we can figure out how many iodides there should be, because we know the charge on magnesium is 2 plus, therefore we're going to need 2 iodides. So if somebody said magnesium iodide, you already know it's going to be MgI2 because we need 2 iodides to balance out the positive 2 charge on magnesium. And so not diiodide. It's not diiodide. We can figure out the ratios based on charge balance, because compounds like acids should be electrically neutral. So we got to find out what the correct ratio is. For molecular compounds, it's a bit more tricky. For molecular compounds, like carbon monoxide, carbon dioxide, they don't necessarily consist of the same charge. What is the typical charge on carbon? The typical charge on carbon is either going to be +4 or -4, but taking away 4 electrons is not so easy. The more electrons you try to take away, the harder it gets. And so sometimes you don't take away all the electrons. So for example, in carbon monoxide, what is oxygen's typical charge? -1, -2, -3, -2. And that means carbon must be +2. However, in carbon dioxide, we have 2 oxides. This is not molecular oxygen. Right? This O2 is not the oxygen that you breathe. If it was, then carbon dioxide should sustain life. It does sustain plant life, but it should sustain human life. But anyway, this is not the oxygen you breathe. This just means that we have one carbon and two oxides. If we have two oxides, then what is the carbon's charge? 4 plus 4. And so plus 4 is it. Have you ever heard of carbon trioxide? Let's say, you know, if this were, you know what I'm going to write here? I'm going to write 4 plus in quotes because, you know, it's not what we call a single ion. So let's put that there. If I tried to throw in a third oxygen in there, what would the charge on carbon be? If I tried to throw in a third oxygen and tried to form carbon trioxide, you know, because let's say if you don't burn it very well, you form soot, right? Not enough oxygen. Make sure you get more air. And so you add more air, you might get some carbon monoxide, but carbon monoxide is bad. Like, you know, a lot of people end up dying every year from carbon monoxide from poorly adjusted stoves and poorly adjusted ovens. You know, if you see yellow flame on a stove, then you know you're generating carbon monoxide, right? Or a furnace. You know. Instead, you want a nice, not yellow flame, you want a nice blue flame, and that way you're going to get minimal carbon monoxide. A nice blue flame should be producing carbon dioxide, right? But what if I just open it even more? And just even let even more air in. If I let even more air in, shouldn't I get better combustion and form carbon trioxide? Well, after carbon trioxide would come carbon tetraoxide, and then maybe some carbon pentaoxide. Depending on if I really open the holes really big on this, I might be able to get carbon pentaoxide. What do you think? Do you know where it stops? Maybe carbon nona or carbon decoxide? Where does it stop? Maybe carbon dioxide is such a big problem. Let's get rid of that and just form carbon trioxide instead. The carbon trioxide would be a worse greenhouse gas. Based on the there are more vibrations. You can have 4 atoms than with 3 atoms. More vibrations. More ways to move. The more vibrations, the more heat that gets trapped in. Heat being infrared radiation gets trapped in. There's some recent article about tundra defrosting in Kazakhstan or someplace. One of the old Soviet republics. There's a tundra defrosting. This just came out last week. It's releasing nitrous oxide into the air. Nitrous oxide, they're saying, is way worse than some of the other greenhouse gases. But anyway, that's all the vibrations. So maybe these are going to be much worse. Maybe we don't want to generate those. But you know what? What the charges I gave you the other day, what were the charges? You know, on the charges I gave you for carbon, I had written +4 and -4. Those are the extremes. +4 is the extreme in positive charge, -4 is the extreme in negative charge. So we expect something in that range. So +2 is okay. Here, this is 0 actually, on the charge. But if I went to carbon trioxide, what would the charge be? Well, on the carbon, what would the charge on the carbon be? Plus 6. And so the only way I can deal with that is, well, what's the maximum positive charge on carbon going to be? Plus 4. If that's the max, then, and I throw 3 oxygens on there, this whole thing better carry a 2- charge. Then it's okay. But I'm not going to get a plus 6 on the carbon. I can get a plus 4 and keep it neutral by having 2 oxygens, or I can keep it plus 4 and have it as an anion. What's the name of this anion? Carbonate. And so the question comes about is this: can you burn soot? Does soot burn? Can you burn soot? Or you know, soot. What is soot made out of? Carbon. Do you know what charcoal is made out of? Charcoal is mostly amorphous carbon versus crystalline carbon, like graphite. Charcoal does have graphite in there. Does charcoal have diamond? It would be nice if charcoal had diamond in there. You can dig around and find diamonds, but you're not going to find much diamond. It's mostly amorphous carbon in charcoal. Can you burn charcoal? You know, yeah, people buy it and burn it all the time at barbecues. And so you can burn it. You can burn soot. And so this is what some people do. Some people's pots and pans are so sooty, do you know what they do? Rather than trying to scrub off the carbon deposits there, they burn them off. And so I know somebody who says, oh, I have the great method for cleaning. And my great method for cleaning is the person leaves it on the burner overnight and burns off the deposits. I wouldn't do that because, you know, it might generate some of this carbon monoxide. But yeah, soot burns. Hey, does carbon monoxide burn? Not very well, but carbon monoxide also burns. Right? You can burn carbon monoxide, you can burn soot. Can you burn CO2? Does CO2 burn? The answer is no. CO2 doesn't burn. This is where it stops. And so this is something, you know, these are like observations, right? These are observations that we want to understand more deeply. We see this pattern here. And so we can start making some connections here with the pattern. And so we might think, oh, is there a percarbonate? It turns out there's no percarbonate. You know? There's no percarbonate. Why? Because if you add an extra oxygen and keep the charge the same, what would the carbon be? So if you add an extra oxygen and keep the charge the same, the charge, it's got to be plus 6. The net charge would be 2-, so we'd have some left over charge. So it'd be plus 6. There's no percarbonate. How come there's perchlorate though? How come there's perchlorate? Well, what was perchlorate again? Cl with how many oxygens? 4 oxygens. And so we have these 4, each one is oxide, right? Which means in perchlorate, what must be the charge on chlorine in perchlorate? Because this whole thing has to add up to this plus this must equal the net charge. You know, so if I take the total negative charge, which is -8, and the total positive charge, which is whatever, I'm going to get the net charge of -1. because perchlorate, remember ClO4 minus, there has to be a leftover negative charge. And so what must be the positive charge on mine? +7. What is the maximum positive charge on chlorine? +7. Well, what about chlorate? Chlorate was ClO3 minus. Well, chlorine wasn't at its max there. Chlorine, 2 minus, 2 minus, 2 minus, which means the total negative charge, which is -6, plus the total positive charge is got to equal -1. That means chlorine was +5. And so chlorine wasn't at the max. That's why we have a perchlorate here. There is no such thing as percarbonate because carbon's already at the max at carbonate. We can't go any farther. And so these are things we're going to talk about in more detail pretty soon. Pretty soon. How about a perchlorate or hyperchlorate? A hyperchlorate. Does a hyperchlorate exist? No. We're maxed out. And so not everything shows a not everything shows a hypo, you know, just certain species do. And not everything's maxed out at 8, you know. The reason why it's chlorate is like this is because perchlorate is pretty hard to get. It's not that stable historically. So we'll talk more about that later. And so this is the way I visualize it. So when I look at magnesium iodide, I see 2 iodides. I don't see a molecule of iodine in there, you know, and that would be quite a bit different. What type of structure do you think magnesium iodide has? Do you think it has a molecular structure or lattice type structure? A lattice structure. This is the lattice. This is different ways of visualizing this lattice right here. This is a lattice structure. Whereas iodine, let's look at if we can have solid iodine here, I2. I2 forms nice crystals as well. Normally it's a solid. These are crystals of iodine, these nice purple crystals here. And so if we look at the structure of that, how it's built up, then what we see is we just have these iodine molecules packed together in a crystalline lattice like this. This is also a lattice structure, but it's different. We would just call it a molecular solid, even though it packs in a crystalline lattice like this, because these molecules aren't connected to each other. Whereas, what was that, magnesium iodide, you know, they're all connected. And so this makes iodine very soft compared to magnesium iodide, which is a lot tougher. So we call it magnesium iodide. When would we call it diiodide? We would call it diiodide if what?
Binary molecule.
Yeah, if both of them were non-metals, then we'd call it diiodide. If both were non-metals. And so we have unusual molecules like this. ClF2. You know, when you look at that, does that really consist of the ions that you're familiar with? Maybe fluoride, you know, just looks like fluoride. But what would this cation be? This cation would be kind of bizarre. It'd be Cl with a 2+. So rather than losing, what's the max number of electrons that chlorine can lose? +7, or 7 electrons. In this case, it's only lost 2. So that's okay, but how would you name that, you know? Well, different ways you could name this. You could name this chlorine, Roman numeral fluoride. But you know, that's usually a name that's reserved for what? If I call this chlorine 2, chlorine Roman numeral 2 fluoride, we usually use this nomenclature system for what types of compounds? Ionic compounds. Is this an ionic compound? Or no. And so rather than calling chlorine 2 fluoride, we're going to call it chlorine difluoride. Now the problem is people mix the rules up all the time. So some people will use a hybrid method where they'll name one using one system and the other. So oftentimes I'll see this, chlorine 2 difluoride. So they're using this one for the first element and then using this one for the second element. And so you can't mix and match. You have to do it. So this one is going to be, what's the name of the cation? Silver, and then this anion is nitride. And so we have two names for this. We could call this silver nitride, or is silver fixed or variable? It's fixed. So we could call this silver nitride, or we could call this tri-silver nitride. Which one would it be? Or we could call it tri-silver 1 nitride. You know, and then we're getting it all mixed up. And so the correct answer for this one would just be silver nitride. And we don't need the tri. The reason we don't need the tri is because we know the charge on nitride is 3 minus. If we know that, then we know we need 3 silver ions, which are fixed charge of +1. This one, manganese, is that fixed charge or variable charge? That would be variable charge. Do you know what the charge on manganese is? Yeah, it's going to be 2+. And so this would be manganese, Roman numeral 2, dichloride, or manganese, Roman numeral 2, chloride? Chloride, yeah. So manganese 2 chloride. So we talk about acids. Let's move on to the next one here. Acids contain H+. But historically, an acid like HCl contains H+. The H+ is pretty reactive. Water is an interesting compound, though. Water can either act as an acid or what we call a base. The base is the opposite kind of thing of an acid. And we have something called hydronium. I don't want to talk about hydronium right now, so I'm going to skip hydronium. The reason I don't want to talk about hydronium is none of the compounds will ever show you hydronium as the cation, and we're just looking at nomenclature right now. When we talk about chemical reactivity, we'll talk about hydronium, so skip that slide for now. How did they name these acids? Well, let's take a look at the name based on the anion name. Okay, what's the anion name? Carbonate, and it goes to carbonate. What's this one?
Nitrate.
Nitrate goes to, okay, what's this one? Phosphate should go to phosphic, but it doesn't. And so why doesn't it go to phosphic? The reason it doesn't go to phosphic is just historical. It doesn't sound as good maybe as phosphoric, and so they throw in an extra syllable in there. And so watch out, because if you were to strictly stick with the rules, you would have called it phosphic rather than phosphoric, because it's phosphate. The same thing with this one. What is this one? Sulfate. So sulfate should technically form sulfic acid, but it doesn't because it doesn't sound as good as sulfuric. sulfuric acid. It's historical. It's kind of a hybrid between common and a name using the rules. And so phosphate gets changed to phosphoric, sulfic gets changed to sulfuric. What's this one? Chlorate gets just changed to chloric acid. So that's fine. And so just these two are kind of different than what you would have expected, strictly following the rules. You know, when we look at this, the group tells us the max charge here. This is group 4 or 14. What's the maximum charge on carbon? +4. This is group 5, which means the maximum charge on nitrogen is +5, maximum positive charge. Phosphorus is in group 5, maximum positive charge on phosphorus is +5. Sulfur is in, you know, and so let me ask you a couple of things. You know, these are little patterns that you might notice if you look at these things for a long time, but okay, this is sulfate. Do you expect persulfate to exist? Yes or no, and why or why not? Does persulfate exist? What would your answer be? No. Persulfate doesn't exist. And why? Why wouldn't persulfate exist? I'm sorry?
It's not in the 7A group. Chlorine?
No. It doesn't have to be in 7 to have a per, necessarily. I mean, that's not the reason why. But yeah, for sure, group 7 has per. All of the group 7 have per. There's going to be perfluorate, perchlorate, perbromate, periodate, and per AT, but AT is radioactive. Don't really worry about that. And so what's the total negative charge here? -8. And that plus the total positive charge must give us a net charge of -2. And so the charge on sulfur must be +6. What is the maximum positive charge on sulfur? +6. Therefore, we can't have persulfate because it would exceed the maximum. Now, what is that maximum? Is that a rule? Is that a law? Is it a rule of thumb? What is that? And so this is why we need to explore. We see a pattern here, and so we'll need to explore, you know, the structure, composition in more detail, theory, whatever, in more detail. But for right now, we just want to learn some of these patterns. And so does persulfate exist? No. Why? Because that would exceed the maximum positive charge of sulfur. That was what we observed. And it's pretty good as far as, we could call this a law of maximum positive charge. Perhaps. Okay. Acids, we talked about that. So this is chlorate, which forms chloric acid. This is bromate, which forms bromic acid here. Skip these. What is the name of this anion? TeO3. What's the charge? Can you tell me the name and the charge? So TeO3 charge is -2. What's the name of it? Tellurate is wrong. What is tellurate? Tell me what tellurate is. TeO4, but not 3 minus. TeO4, 2 minus. If tellurate is TeO4, 2 minus, then this must be tellurite. If this is tellurite, what do we do for the acid name? Tellurous acid. What is the name of this? This is tellurous acid. Tellurous acid. What is the formula for perbromic acid? Well, we're going to work backwards here. They're giving too many clues. I wouldn't give this many clues to you. But if we have perbromic acid, then what's the anion? Okay, perbromic acid, or if you can't see this, would have the anion perbromide, perbromate, or perbromite. Which one would it be? Perbromate. And so what is the perbromate? Well, we memorize bromate. What is bromate? BrO3 negative. So perbromate must be BrO4 negative. And so for bromic acid, this must be HbRO4. That would be it. For bromic acid, HbRO4. Okay, we'll take a break right now and then we'll start.